Professor Ofer Lahav.
Well, good to see you all. Thanks very much for the kind invitation to give this talk, and I'm sorry I'm not there in person due to the train drive. So I hope you can hear me well, and what I'll do now, I'll share the screen, right? I'll share the screen. I hope it's yeah, can you see it?
Yes.
And I'll put it on full screen mode. Is this okay? Can you see this?
Yeah.
Excellent. So let's go straight into business. I know it's quite a busy day for you, many different talks, many different ideas. My line in this talk is actually to connect two disciplines, namely cosmology and AI, artificial intelligence. So the purpose of this talk is to show you how new techniques, which now are so widely used in other fields, can also help us in astronomy. Incidentally, there's some background noise. I wonder if it's possible to mute it at your end while I'm talking. Thank you. And so that's about this AI for exploring the dark universe. On the left is actually a map that was created by a former student of mine, and this is actually dark matter. If you can see the arrow, this is dark matter. I'll explain it later. This is for orientation, the Milky Way, taken from the Gaia data with large and small Magellanic clouds. So just to give you some indication of where the talk is heading. As said, I work at University College London. Many of you may know the location. It's near Euston, King's Cross, and luckily we're back in face-to-face activities there. And just to say from the beginning, a lot of what I'm going to show was done by dedicated work of PhD students and postdocs of mine over the years. Here is a picture taken at the meeting in Windsor in April 2019, when we were all so pre-COVID, and we hope to have more and more meetings in person in the near future. So you'll see some examples of their work. Okay, so the outline of this talk, as I said, it's about connecting two distinct disciplines, namely cosmology, and specifically dark matter and dark energy, to the world of AI. We'll see what's the interplay. So I know many of you are very familiar with cosmology, but just to have everyone on the same page, there's obviously this picture we have for the universe, namely starting from a Big Bang. We see the echoes of that in the microwave background radiation. You see that it's not uniform. There are fluctuations at the level of 10 to the minus 5. And then is the epoch of reionization. And eventually there are the galaxies and the stars and the planets around us. So big questions, right? What is the origin of structure? How did luminous large structure form? What is the nature of dark energy and dark matter? And at the bottom is a collection. It's not everything, but some of the big projects, the big facilities we have. Some of them are satellites, some of them ground-based. You might have heard Planck for the CMB, Gaia already mentioned for Gaia measures, so 1 billion stars in the galaxy, LOFAR, SKA, radio, dark energy DESI I'll talk about, the optical. Euclid is a space mission, and optical and LSST is another ground-based facility. So we've been very, very fortunate in the astronomical community to have all these amazing facilities going on, and especially the recent ones like Euclid, LSST, it's about $1 billion each. So I'll try to explain to you what is it that make us so excited about this, and that we're thankful to the taxpayer for putting so many resources towards this endeavor. Okay, so moving on, just again, this is very basic stuff, just to remind you that we live in an expanding universe. So if we define ad hoc a box, it will have galaxies in that separation, but after a while, the separation between them would get larger, and that's what we see is the effect of redshift. So an observer on one will see each of the others going away and getting redshifted. And it seems that we cannot avoid this bizarre concept of Big Bang. You know, each time I talk about it, still think I'm telling you science fiction, but it's not science fiction. There was a Big Bang about 13.8 years ago, 13.8 billion years ago. 13.8 billion years ago, there was a Big Bang, and we see the echo of that in the cosmic micro background. And soon, within the first 3 minutes, we got the first elements, the nucleosynthesis done, and the universe is still expanding. And not only it's expanding, it's actually accelerating. So this is kind of what's going on. You may recall the two groups measured supernovae. The supernovae are exploding stars. It's usually a combination of two objects, and when one accretes a lot to the other, there's an explosion, and we can use them as standard candles. So we assume that they all look alike, and therefore the further an object is, the fainter it looks, and we can do the inverse of that problem and tell the distance and therefore the geometry of the universe, and therefore whether or not it's accelerating. So this is actually real data, and we are the present, let's say, we are the present, and we can only observe the past, we cannot observe the future. But if those measurements are correct, and people have tested them over 20 years now, because the original measurements were taken place over 20 years ago, it seems that they would sit on the line which looks here orange, accelerating universe, and not, for example, on the green line, which is the critical density, which was the model believed when I was a student. When I was a student in Cambridge, we were told it's a green line. And then I was lucky enough to see a paradigm shift, a change, due to this data by two teams, and it gave them the Nobel Prize 2011 to discover that the universe is actually accelerating. So this has led to lots of activity in the field and to all this ambitious project that I showed you. So it seems now that we live in a universe which we like to call lambda CDM, lambda plus cold dark matter. Lambda is the cosmological constant, and which might be maybe a more complicated concept. So some people like to call it more generally dark energy, and there is cold dark matter. Now, the great success is that really, if you go to conference after conference after conference, almost everyone will show this pie diagram and would tell you that the universe is made of about 5% ordinary matter, 25%, let's call it dark matter, cold dark matter, and 70% dark energy. So everyone agrees on that phenomenologically. Everyone agrees if that's the measurements you do, that you get. That's an example of the fluctuations of the measurements. P, this P of K, it's a square of Fourier modes against wave number. If it's too technical, just think of it of the amount of fluctuations against scale. These are actually small scales, these are big scales. And you see most of the points, admittedly with error bars, go through the line, which is this lambda CDM. And the data come from Planck, the cosmic micro background, from galaxy surveys, and from the position of galaxies, and from gravitational lensing, which we'll see in a minute. So it's quite a bizarre universe that actually everyone agrees about this menu of 5%, 25%, 70%, but we have no clue what dark matter is, we don't have no clue what dark energy is, okay? So we're in an amazing state of ignorance, but that's what makes it interesting, right? And in this concept of lambda, of course, goes back to Einstein, 1917. And this is Einstein equation, and this is this lambda, on the left-hand side, this is curvature. These terms which define curvature. On the right-hand side is what's called the energy momentum tensor, which defines energy. Today, most cosmologists would say maybe it should have been on the right-hand side, because maybe it's some contributions from a quantum vacuum, so it should be on that part. We still don't know. If you take what's called the weak field limit of GR, you come to our more common type of physics, and then the acceleration is minus gm over r squared. Okay, we know that from Newton, but there is this extra term, this lambda term, which is linear with distance. So in actual fact, this is attractive force and this is repulsive force. Now you may ask, I'm telling you about Einstein, who is here in that picture with his friend Eddington on a sunny day sitting on a bench in Cambridge. Why do I show Newton? Well, it's not well known, but actually Newton also talked about force which is linear. He didn't call the constant lambda over 3, but he does talk about it. It's in Principia, and he was very excited about it. And if you look at my website, we wrote a popular article about this some years ago, which tells a story. Einstein put lambda for a different reason. He wanted a static universe, and when he discovered that the universe is actually expanding, he thought it was the blunder of his life. But then Eddington, his friend, actually liked a lot lambda, and he said he's a detective in a search for a criminal, lambda. So, you know, this lambda business has been quite a topic, and it certainly kept me busy myself over many years, and many of my colleagues. For those who want a bit more information, I put a popular article in a magazine called Contemporary Physics. It's also in that, you can see it on the archive. It's just a popular article. There are many popular articles, but this is my version of it, and basically I asked the question, is it just lambda? And what it is, you have to define an equation of state for any substance. You define the equation of state, and you call the ratio of pressure to density, c squared is the speed of light squared, you call it equation of state, and if you do textbook cosmology, you'll find density goes A scale factor minus 3, 1 plus W. For matter, W is 0. That's quite intuitive that as we start from the universe, from early times, high redshift, and as we go through time, the density of matter gets diluted, like a to the minus 3. It's like a bit should remind you 1 over volume, sort of. You can ask the question, for which W I'll get a constant energy, which is what the lambda is, and it turns out for lambda exactly minus 1. Okay, you can see that. It's minus 1, rho is a constant, it's that line. And the universe started accelerating when it was 6 giga years old, 6 billion years ago. Remember, solar system was formed more or less here, 4.5 billion years ago. And dark matter, dark energy became equal at about 3.5 billion years ago. So now we're in a period, that's the blue dot here, when 70% is dark energy. So it dominates the universe at present. So what do the measurements show? I'll explain it a bit more, but Dark Energy Survey and Planck and BAO and so on, they give a number for W which is very close to minus 1, but not quite. It's to within 3%. So we're now in this period of the field that we know it's probably very close to minus 1, but if it deviates from minus 1, you know, this would be another Nobel Prize, right? It will be a big shake-up for physics. So that's why we still want to invest in all these $1 billion projects to pin it down. You know, I'm happy to get questions on this later. I'm sure what I said could be seen as quite provocative, you know? Put billions of dollars to tell if something is that close to minus 1. Now, not everything in this picture is that rosy. In actual fact, when we look at the Hubble constant, which is the rate of expansion, Hubble constant is the ratio of recession velocity to distance. It's appropriate to call it Hubble-Lemaitre law, because Lemaitre also worked on that. And the question is, what is this constant? And when I was a student, there was debate, is it 50 or 100? in units of kilometer per second divided by megaparsec. Because distance is megaparsec, velocity is kilometer per second. The question was, is it 50 or 100? Now the question is it 72 or 67? And there are very heated debates over that question. What is it? And you can see some examples here. And the answer is we don't quite know. Several of us did with colleagues. We did a review article recently, about 40 pages. You can read it. And likewise, with discussions about COVID and other things, we went for a traffic light scheme of each method. And when we say red, it doesn't mean it's wrong. It just means you have to do more work on it. So in some techniques, there's just not enough data, okay? For example, gravitational waves, there's only one good object to do it with. So we would like to see more. I don't go through all that. I just want to give you a flavor that the model is not perfect, right? Which is why we have to do more work with billions of galaxies, which is why we need AI. Okay, this is the logic of what I'm trying to get through. You probably heard about gravitational waves, and you can see, this is the core of the galaxy, NGC 4993, and if you can see it well on the screen, you'll see an optical appearance of a dot, and that's the optical flash, optical glow from this remarkable gravitational wave event that happened in August 2017. So all that is really very exciting. And also what this has shown us, this is what it was seen by half a dozen or so optical observatories, but what's remarkable here is that this also allowed us to measure the speed of gravitational waves, which turns out to be the same speed of light, and this also was used to reject many models. This is some work by a former student of mine, Tonella Palmassi, actually using the getting Hubble constant from these gravitational waves, and some of them are what we call bright events, like we could see an optical flash. Others we cannot see if it's black hole, and we have to use some other inference, so that's error bars are big. But that's an example of a red light in that diagram of what we can do. So how do we actually measure dark energy? There are standard candles already alluded to supernovae. So if you think of each supernova as a candle, if they're standards, those further away will look dimmer, and therefore we can take the distance. You can do the same with standard rulers. These are features in the galaxy distribution, which are called baryonic acoustic oscillations, BAO. You can use weak gravitational lensing, another effect that Einstein predicted, to actually look at how light propagates. So what happens is that distant galaxies, say this one looks like an ellipse, and it will look as a very thin ellipse when we observe it, because the light got bended by intervening matter. We don't know, of course, what's the true shape, but we can do it statistically. And cluster of galaxies also bend the light, and we can use that. This is a picture from Hubble Space Telescope. We can use that to weigh clusters. So, as I've already said, this has led to many activities in the field, and the funding agencies were actually very supportive. So there are two projects in which I've been involved quite a lot at UCL and also the UK. There are American-led projects. One is called Dark Energy Survey. One is called Dark Energy Spectroscopic Instruments. Very confused, DES and DESI. But we're involved in that, and in fact, there are 5 big lenses in DES and 6 in DESI, and they were assembled in our basement at University College London. Other collaborators in the US and elsewhere built the CCD system for DES, for example. Each of these is a 4-meter telescope. And this is the next generation, LSST, now named after Vera Rubin, a distinguished American astronomer, and Euclid, which is a European Space Agency mission. So we're using current surveys to pave the way for the big ones. And these are some numbers for you. DES, DESI, Rubin, Euclid, SK is a radio telescope. You can see we got lots of data, right? 1 terabyte per night on DES. It will be 1 petabyte per day on SKA. You can see number of galaxies goes from Again, when I was a student, we used thousands of galaxies. Now my students can use hundreds of millions, and soon it will become billions. You can see the cost goes up, so I like to tell travel agencies that it's only $1 per galaxy, so it's a bargain. And also the number of scientists go up, and we work now in teams which exceed 1,000 scientists. So this brings all kinds of interesting sociological and anthropological questions, which I'm happy to answer questions about it later. And this is, in short, the tale of those two surveys. I already said quite a lot about them, just to emphasize that with DES, all the data have already been collected, and DESI is producing data as we speak, more or less. And I mentioned the contribution of the UK and UCL to this. We have several institutions in the UK involved in DES and in DESI. I don't know if you're physically in Nottingham. Nottingham is also a member of DES, and there are other universities in the UK. This is this dark energy survey, which makes use of all these techniques. I already said 300 million galaxies in the bag, thousands of supernovas, so you can check this acceleration idea. And there are over 300 papers in the literature. And as mentioned in the introduction, I co-edited this book. And this is the story of the survey told by the insiders, told by those who created it. And we even allow ourselves to have a section there about anthropology and philosophy, and there's even a poem. So this can tell you the whole story, which I just compress into a few minutes. And this is DESI, which is spectroscopic. Okay, DES is photometric. We measure things through photometry, and DESI is spectroscopic. And that is to measure 35 million spectra using 5,000 optical fibers. And we're pleased to report already 12 million spectra have already been measured. So I'll show you just a small, I hope the animation will work. This is animation created by a student of mine, Joshua Williamson. And this is only 500,000 of the 12 million. If you plot all 12 million, it's so dense you can't see much. So let's see if it's going to work. So this is in slices of declination that go from the north to the south. So each time we project a slice, which is 5 degrees wide. So just to give you kind of an impression of it. And you can see what we call it the cosmic web in full glory. Galaxies are not distributed uniformly. They are clumped. So all is wonderful, except that last week there was a fire on the mountain of where DESI is. You might have seen it in the news. Luckily, we're continuously in touch with the team there, and luckily the effect on the telescope was not severe, and there's discussions about resuming observations. But you can never predict. I was caught when I went observing for DES. That's on a telescope in Chile. Okay, so DES is on a telescope in Chile. DES is on a telescope in Arizona, and I went observing in Chile. And on my last night there was an earthquake of 8.3. Okay, and again the telescope survived over there. So these telescopes, which were built in the 1970s, seem to be very strong and can cope with earthquakes and fire and other disasters. But of course, we have to guarantee that the expensive instrumentation on it, on DES, there's a camera of about $40 million, and DESI is even more expensive, 100 million. And of course, it's, you put so much intellectual work into this over so many years. So don't worry, I know these pictures look very dramatic, but the impression I get is that things are going to be all right, and we'll resume observations. So finally, I can tell you about AI, okay, because I promised you that this is some combination. So I hope you fully understand why astronomy is so much ahead in the game in data, because we've been using data all the time, and it's increasing. So AI was pioneered by Alan Turing. The term was coined in 1956. You can think of it as a branch of computer science, but of course it does touch many other things, and some people talk about big data, machine learning. There are different terminologies here, and the new kid on the block is the so-called deep learning, which I'll talk about in a minute. Now, some people talk about big data. Now it's more trendy to talk about data science or data-intensive science. So by complete coincidence, I came across this cartoon the other day, which I found quite interesting. So I thought maybe I'll try to explain the difference between big data and data science. So the difference is, in this case, the data are all these pieces of bread, okay, which a kind person is giving to the ducks in the river. So that's the data, okay? But the data by itself is not interesting. It's what you're asking. That's why we call it data science. So how do you analyze the data? So here you can see a statistician who is saying how much bread is there. So it's not just looking at the points, it's actually counting them. The geographer wants to know where is the bread. The psychologist wants to know why do they give us bread. It's a different question, right? You need different tools, you need different algorithms to answer that. The astrophysicist says, is there bread on other planets, right? So you have to do a different type of analysis and compare the Earth to the planets and this, so on and so forth. And the philosopher that's a bit outside my scope, at least for this talk, is asking, is there more life than bread, okay? So here you are. I thought it's kind of interesting and thought-provoking. Food for thought, as you may say. Okay, now I like to think of the whole story actually not as AI, as artificial intelligence, but as augmented intelligence. And I'm thinking of it, not only me, but colleagues and so on, about connecting laws of physics, which are probably there whether or not we exist, this philosophical question, human knowledge which was accumulated, for example, Einstein's theory, Newton before him, Darwin's theory, things like that, and some tools which could help us to understand even better. So I like to see this connection, but it's of course a matter of taste. Some people would tell you robots will do everything. We don't know. So there are all kinds of techniques. There is supervised versus unsupervised. That's when you actually teach the computer the different knowledge, right? So you tell the computer what's a cat, what's a dog, and then you show with some new data, and it can tell you what's a cat, what's a dog. But you can also unsupervised, let the data speak from themselves. There is this, as I said, new kid on the block, deep learning, which has transformed the subject. And that shows you don't extract parameters of the dog and the cat. You don't extract, for example, the shape of the eyes of each of them, but you show the whole picture of the dog, the whole picture of the cat, okay? And applications are numerous in astronomy. You can imagine, instead of cats and dogs, you can separate galaxies from stars, the different types. You can classify the supernova I talked about. You can classify gravitational waves I talked about. You can predict distance, and you can predict properties. And you can also use it to derive the underlying parameters of the universe. You can also use it to improve simulated data. We call these emulators. So I apologize for jargon, but I hope you get the idea. There are many questions. Is it just a black box? And if not, how to explain, connect it, for example, to Bayes' theorem, which is written there. How to minimize biases. If I only show cats, how would this algorithm ever discover what are dogs, right? It wouldn't know. It might say that there's something different, but it wouldn't call it a dog. It just doesn't know. So there are all these questions about introducing physics or not. And I remember when I entered the field where it was complete fringes in the early 90s. And I remember a nice statement in The Economist magazine, only if you know how to make money with machine learning, only if you know how to make money without machine learning, you can make money or even more money with machine learning. So I'm telling that to my students, okay, that don't just take something off the shelf, run it, say great, try to relate it to something else you understand, and don't lose intuition. I mean, we were given this gift by nature that our brains can actually think and connect information and so on and so forth. Okay, I just want, this is the kind of work we did in the 1990s, where we sent 840 images of galaxies to 6 gurus. Unfortunately, some of them are no longer with us. And they classified them into a system of 15 steps. It's called the Voculaire T-type. He was actually one of them in classifying it. And what we showed is that you can actually classify reliably objects with a computer. This was later extended in a big way in the Galaxy Zoo, which you may have seen. So I think, we showed quite 30 years ago or so that that's possible to classify galaxies. And this is the latest using Galaxy Zoo. I hope you get the idea. You observe, here's the galaxy, a human tells you that it's a spiral galaxy, but you also extract parameters, 10, 20 parameters. You feed it into an artificial neural network, which is some nonlinear function really, and you ask, it has 3 parameters, they get minimized, and therefore you can educate the algorithm based on the examples, and then you show one example of an actual object, and it tells you what it is. A cat or a dog, or a spiral galaxy, elliptical galaxy. And you can see, if you have only 2 types, you can easily get it about 90%. Of course, you'll have anomalies, you'll have outliers, but they're interesting by themselves, so you also learn about them. And this is another example where computers could detect arcs. This is effective gravitational lensing, arcs around objects. This is on simulations, but they've done really, really well, okay? So, you can get, again, 90% or so. And this is a way of measuring redshifts to galaxies, even if you only know you have the information through a certain, this is flux against wavelength, and these are, if you put filters, I know some of you take pictures of the sky and you put different filters. So here it's the same, you put filters, 4 or 5 filters, and therefore the portion of the spectrum that will go through the filters would vary from one filter to another. And this, you can do an inverse problem, and about nearly 20 years ago we did this algorithm using machine learning. You put the magnitudes in, and you have a redshift out, and all that's happening is this complex structure is just a nonlinear function, okay? Redshift is function of those magnitudes. And there are many techniques now. It's very, very important. It's at the core. All these projects of billions of dollars need those techniques. All those photometric surveys, you all need these techniques. There is something else which maybe is a bit more intuitive, which is called decision trees, right? We're used to it all the time, right? We get to the end of the road, do we turn left or right? Or maybe go straight at the roundabout. So we take decisions, right? And the same thing, you can classify plants or trees or cats or dogs by asking questions about certain parameters, okay? So again, if you have an example of the true answer, the method will actually find what are the parameters. If something bigger than something, you call it class A. If it's smaller than something, you call it class B. So you have this decision tree, and you can have one tree that found that it's class B, but you can have another tree which got it differently, and it got it A, and this one also A. So you can now average it, and that's why it's called forest, okay? And then you tell the user the actual answer, right? You tell at the end, is the cat or a dog, is this, this cell affected by cancer or not? These sort of things. So what is this deep learning that I kept talking about, is in the old days we'll do what's called some people call shallow learning. You take an object, you extract features from the object, and that's what you feed in. That's what we did when we classified galaxies. We had 10, 20 objects. Now, the thing about deep learning, you feed the whole image all together, so you don't have to do feature extraction. You can see what happened in the field. This is the number of papers with this idea, or even more generally, machine learning in their title. And, you see it's very flat. We started doing work on this long time ago, 1990s, but suddenly, about 10 years ago, there was a big jump due to this deep learning. And in our field, about every 4 days, someone writes a paper with deep learning in the title. So it's very topical. And what is the trick again is that you take the image and you convolve it with masks, okay? So you put all these different masks, and you can ask correctly, how do you decide about this mask? So there's some guidelines how to do it, and that's what goes in. If you like, the pre-processing of the shallow learning is done here. Now, I don't like, I said it here, I don't like to say that shallow learning is shallow, because it's quite deep, because it depends on human knowledge. Because here, if there's a biologist, they would tell us, look, this part of the image is very boring, but this region, there is something which is the eye of this creature, is very important, right? So I don't like to say shallow. I think you bring in human knowledge in. This is an example of getting the redshifts. This is a former student of mine. He just finished a few months ago, and he's part of our new, in fact, he was among the first in our new program for data-intensive science. And here it's difficult to see, but this is the redshift derived by these methods against the true redshift. And what Ben has done, he tried to give it just 4 or 5 numbers, the magnitudes, but you also gave it the full image. And indeed, if you give the full image without pre-processing, you get an improvement of factor 2 in the square of the error. And another student in the same program, Prof, what he's done is to actually try to understand what is it in that picture that makes us think that there's a bar here. I don't know how well it comes on the screen at that end, but is there a bar there or not? So this is the trick is we create kind of what's called saliency maps or sensitivity maps, taking the output of the algorithms, take derivative with respect to the input. And it's very nice, it does actually pick a bar, and you can even measure it and plot it against measurement of a bar by an astronomer, and you see this good correlation. So it suggests we can use that to measure bars, to actually measure the size. Okay, this is just to say there have been many, many techniques. Now, if we move to galaxies to characterize the distribution of galaxies, lots and lots of statistics, and we want to move again from the more naive techniques, more basic techniques, to the neural networks. And this is, you know, you can look at distribution of galaxies, but you can also look at distribution of dark matter. Now you're going to ask me, how could you see dark matter if it's dark? So I told you in gravitational lensing, there's this effect that objects, remote objects, would actually look distorted. Okay, the intervening mass takes an object which says an ellipse in reality, and you see it as a banana shape. So you can do the inverse. And what we've done with Dark Energy Survey, using 100 million galaxies with shape measurements to infer the mass map, and this was led by my former student, Niall Jeffrey. And this is the plot I showed on the first slide. This is the whole area of DES, but at the moment using only half the data, so there will be a better map. Year 3 here means data from the first 3 years. And this is the inverse. This is a result of the inverse. So ignore the Milky Way here. This is only for orientation. But what you see here, regions which look yellow have high density, and regions which have dark have low density, and that's how you get that distribution. For those of you who like mathematics, it's an inverse problem. Gamma are the distorted images, these bananas, and kappa is the projected mass times something which tells us the basic cosmology that connects the two, and n is the noise due to the shapes. So we released this map in May, just over a year ago, and the BBC liked it, so the map, and some of us appeared in both TV news, BBC One, 6 o'clock, 10 o'clock, but of course the ultimate achievement was that the same week, Private Eye was inspired with this cartoon, and maybe you can read what it says. It's our most comprehensive dark matter map yet. So here's a great compliment from Private Eye. And as you can tell, we're doing much more of that. And we're also connecting the structure we see there to actually distribution of galaxies. So in the remaining few minutes, I hope I'm keeping all right the time. I'd like to tell you about education, because the world has changed a lot, and we are swamped with data, and it's clear that the next generation of students should get education different from the one I got, because they are developing in a new world. And we're very fortunate that the Science and Technologies, STFC, Science and Technology Facilities Council, has helped us to set up a center for doctoral training in data-intensive science. You see, I don't use the word big data. I call it data-intensive science. And we already had it running for 5 years. We just got a new grant alongside other centers in the country. It was a very competitive process, and we got a grant to continue it. So far we had 53 students going through the system. 10 of them already graduated, and they're doctors now. And what's unique about this program, they do their astronomical work or high-energy physics work. They might be a project at CERN or a project on dark energy survey and so on. So they get a PhD in physics, but they also spend, of the 4 years, they spend half a year working in a company, in the industry. Okay, and we have logos here of different companies. Some of them are, government agencies, some of them are private. You can see big names of companies such as Intel, for example, ASOS, a fashion retailer. So it's quite a lot of fun. These students get a dual education and dual career, and I can tell you the companies really like them, and some of them recruit them straight away. So I think it's quite an interesting program. We also have a parallel one in masters. This is a zoom in on these companies, so you can see IBM and Nvidia and NHS and so on. And of the 53, I was very, very fortunate to work with 5 of them, and I've mentioned some of their work. This is Konstantina and Ben and Sunil, Prab and Joshua. You've seen some snapshots of their work. So all that is really great. And as a final thing, we also have all kinds of other activities for wider participation, and we got a special grant to do a project with Jordan, which I'll talk about in a moment. We also got support from our university to set up this center, which I have the fortune to co-direct, and we have this PhD program. We have an MSc program with about 70 students per year. We have the 30 or so industry partners. We have the international activity, and of course we have research and connected to different activities in this field within our universities and outside. And I mentioned this project with Jordan. So this is building that capacity for data science in another country. And we received a nice grant from the Research Council 3 years ago, but obviously we could not travel, they could not travel, so we did it remotely, and we had some taught courses. There are 2 cohorts that benefited from it. Incidentally, over there, 60% female. So it's very different from the picture we see in the UK. In similar fields, you have 20-30% female, or 60%. And in fact, we work closely with the British Embassy at Amman, and in fact, we're very pleased that we're going finally to host a summer school in person in July. They're actually coming in July. 29 of them are coming, and they will be doing different projects and so on. 7 of them even come earlier, in fact, as soon as Monday, to work on projects. So this is very exciting for us as something different, where you take particular knowledge and spread the word. And I personally have aspirations. I'm originally from Israel, so I have some aspirations of spreading it across the Middle East, also having data science as a kind of bridge for peace. I think we can think of data science a bit like about music. It's a universal language, and if one country needs data science to help with astronomy research or with health, why not sharing knowledge across countries, expanding it and making more people enjoying it? And I think the most important thing is to invest in the young generation. So I'm just giving you quite a long tour. I think I'm just on time for the 45 minutes allocated. I think I got it right. This is just summary that astronomy is really going in an industrial revolution. It's something completely new. On that scale, we have all these data sets which you have on your mobile phone and all the way to your bigger computers if you work in the industry, or your user of it if you give any services of some sort. We're all users of that. And the challenges are really to understand the algorithms. I want to emphasize that. The risk is of using algorithms off the shelf without understanding it, right? You would like your medical doctor to tell you why is the reason you have to undergo an operation. And there's a question how to scale up algorithms, from thousands to millions and billions. And, it's a great playground to train the next generation of researchers well beyond academia. So I think that's a good point to stop. And if time permits, I'm happy to answer questions now. If not, I'm also happy to receive emails. So thank you very much for listening. It was a pleasure talking to you.
Thank you very much. Go on the camera. Thank you very much, Professor Lahav. That was covering an awful lot of different subjects.